Jnanam paramam dheyam. Knowledge is supreme.
Okay, so today let me just briefly summarize what we did in the last lecture, make you recall all the notations again, and in the process I will slowly take you to basis for operators. You have studied in your first course that momentum operator can be given a differential operator representation, right? Momentum, all the observables can be written as operators. We want to see, just like we want to write a basis set in a linear vector space, we would also like to see what is the basis for a operator. Okay, so that's the theme, and I'll just briefly summarize what we did in the last lecture. State of a quantum mechanical system, we formally denote it as psi. Typically this psi will have evolution in time, so we call psi as a function of time. Most of the time we suppress this t, but this is the state of the system, and this angular bracket is called as ket. So this state, once I give the state, this is supposed to contain all the information about where this system is. What is the state of the system means? It could tell me what is the energy of the particle, it could tell me where is the location, all kinds of informations are all stored in this bracket ket, which is having a state psi. Okay. And we talked about span, can span the space, and you should also make the span such that they are linearly independent. If you have both spanning the space and linear independent states, that collection is what you call it as a basis set for the vector space, and the number of states in the basis set, that defines the dimension of the vector space. So as an example, we were looking at the 3-dimensional space, but you can do it in general and abstract space. Then we talked about that there is a dual vector space, which will denote it as V tilde. In the states in this V tilde, they are given by a different angular bracket and they are called bra. Okay. So this is the Dirac bracket notation, which we are going to exclusively follow. And why do you need these dual vectors? If you have these dual vectors, you can determine scalars by taking, in the conventional 3-dimensional space you would have said dot product, here we will say it as an inner product. So we confined today with finite dimensional vector space, we could go to infinite dimensional, so on. Let us confine ourselves to finite dimensional vector space. If psi, so in this finite dimensional vector space you can denote the ket, you can represent the ket by a column vector. So you can represent a ket by a column vector, let the column vector have n components. So this n equal to 3 is similar to what we saw in the 3-dimensional space, but you could have an abstract n dimensional vector space where n is finite. Similarly, the dual of this ket, which we call it as a bra, some other state, will be denoted by a row vector, that it is denoted by a row vector. Suppose the entries in the n components are x1 to xn, some kind of an n tuple. These x1s to xn could be real if it is a real vector space. It could be complex if it is a complex vector space. So with this two states which I have given in the vector space and the dual vector space, you can find an inner product. What is inner product? In this representation of a column vector and a row vector, it is multiplying a row with a column. We have done this in matrix mechanics, right? Matrices, theory of matrices. A row multiplying a column will give you a scale. So, row multiplying a column is given by the inner product, and that will be a scale. The next question you can ask is, if you write the two states in this fashion, the second line, what is this? It is a column multiplying a row. You have done column multiplying a row. What will that give you? It gives you an n cross n matrices. Okay. So, this is also an allowed operation, but this does not give a scalar, but it gives a matrix. If you represent the states by column vector and the dual vectors by a row vector, the inner product is a scalar. This angular bracket is what we will call it as a outer product. Okay. So, earlier we called the earlier one as an inner product. This angular bracket we will call it as an outer product. So, outer product is going to be giving you not a scalar, but it is a matrix. If the vector space is finite dimensional, n dimensional vector space, then it will be an n cross n matrix. So, in some sense, in the Dirac notation, the outer product can be treated like an operator and which can be represented by n cross n matrices. Okay. So, representation means what? Suppose it is like giving a color to something. Okay. So, it is some kind of, I represent this by a blue color, I represent this by a green color, something like that. It is like different colors or different dresses. You can dress this operation. Suppose I want to look at roots of unity, right. You are all familiar with cube roots of unity, right. Omega is a cube root of unity because omega cube is identity and 1 plus omega squared is 0. You can represent that omega by a 2 by 2 matrix. You can give address to that omega by writing a 2 by 2 matrix. What is a 2 by 2 matrix? It is just rotation about 120 degrees, right. Cos 2 pi by 3, sin 2 pi by 3, could do that. So, this is what we call it as a representation. So, omega cube equal to 1 and 1 plus omega squared equal to 1. I can denote one representation as e to the power of 2 pi I by 3. This is one representation. The second representation is omega could be written as a 2 cross 2 matrix as cos 2 pi by 3, sin 2 pi by 3 minus sin 2 pi by 3 cos 2. So, these are called representations. Why representation? The one which I have written here, it satisfies both these equations. Similarly, the 2 is a different representation or a different dress. It satisfies both those equations. So, given some equations, you can try to write different representations and see whether it satisfies those conditions. Okay. Similarly, a formal abstract state psi which I write, I am giving a representation as a column vector with n rows and one column, right. Similarly, a bra vector in the dual vector space will be denoted by a row vector which is one column and n rows. So, this is what is happening. So, whenever you take an inner product, it becomes a number which is a 1 cross 1 element. If you take an outer product, so inner product psi with phi is actually a number with 1 cross 1, a psi with phi will be a matrix which is n cross n. It's very simple, but if you start getting used to the left hand side notation, you can do many abstract calculation in a very neat and elegant fashion. Always recall with what you know in matrices, and that will help you to remember this. Okay. So, this is what we call it as a outer product. Okay. So, this is the representation if you want. You can represent the ket vector in a finite dimensional vector space by a column vector. You can represent the dual vector, which is the bra, as a row vector. And this is what we conventionally going to follow. For a finite dimensional vector space, we can play around with matrices. So, this is what I said, column multiplying a row is the outer product, and that will give you an n cross n matrix. In fact, we call this to be this outer product to be an operator in the Dirac bracket notation. By the way, you remember that this inner product of the same state is called the norm, and if you try to write it in this notation, you want the norm to be always greater than or equal to 0. When will it be 0? When phi is a null vector. Okay. Otherwise, this is going to be in general positive. And if you try to rewrite in the representations as a row vector with x1 till xn and a column vector with x1 to xn, then this is the condition you will get for the inner product of these two vectors, right, the square of the norm. Right? And because this is positive definite, this will also be, each one is a square. I have written xn squared. Technically this is not correct. When is it correct? When it is a real vector space. If it is a complex vector space, I have to take conjugate and transpose of a column vector, complex conjugate. So, you have to put x1 star, x2 star up to xn star. And this condition for a real vector space, if suppose I take n to be very large, even though I started with a finite dimensional vector space, if n becomes very large, the squares which I add may blow up, okay, may become infinity. So, you need the condition that the summed up quantity, for a finite dimensional vector space you can always make it finite, but if n becomes very large, there are chances that this would not be finite, but you have to impose this condition, take the states in the vector space such that the norm is always finite. We did this in the wave functions. I said that those wave functions are all square integrable wave functions, right? I said this in a week or 2 weeks ago. I said this. Similarly, this condition on a vector space, which is on a finite n dimensional vector space, is supposed to be, the sequence is supposed to be a square summable sequence. If it satisfies this condition, and this collection of such square summable sequence, which are a set of phi 1, phi 2, a set of states which belongs to this n dimensional vector space, that vector space, if it has these kinds of square summable sequence, then you call that vector space, you denote that vector space as L2. So, L2 is, so L2 is a vector space with a set of states obeying summation over xn squared to be less than infinity. The state says technically I should put mod xn because I have not specified whether it is a real vector space or a complex vector space. So, the square integrable, square summable sequence. So, this condition which I have, maybe I should put an I from 1 to n. So, this condition is what we call it as a square summable sequence, that it sums up and it is finite. So, you can slowly see that when you go to in your course in integration, what exactly you do. Initially, if the lattice is spaced, you start doing discrete summations, but suppose I make n to be very large and make it to be a continuum, then it could become a square integrable situation. Okay. So, you can see that I am trying to make it as a finite vector space, but at some point I will start making it as a continuum and look at square integrable functions and states and so on. So, this is just to give you a feel of what exactly is happening in a finite dimensional vector space. This finite dimensional vector space is something which is not, it happens in the systems, right. How many of you have seen Stern-Gerlach experiment? There are actually two beams and those two states are linearly independent and you can have a two-dimensional vector space. Okay. So, it is not that whatever I am saying here is not happening, it happens. So, you do have two linearly independent physical finite dimensional vector space. Okay. So, let me just get to the two-dimensional vector space just for simplicity. Till now I was talking about n-dimensional vector space, but I will now confine myself to two-dimensional vector space and try and clarify a couple of notations, and then you know how to do it for a n-dimensional vector space. So, if you remember, we had two bases in the last lecture. One was a orthonormal basis and the other one was a non-orthogonal basis, right. So, let me just proceed with this example. So, we call phi 1 and phi 2 to be orthonormal bases When is that? When the inner product of phi 1 with phi 1 equal to 1, phi 2 with phi 2 equal to 1 and phi 1 with phi 2 equal to 0, phi 2 with phi 1 also equal to 0. This can be compactly written as phi I, phi j equal to delta ij. For a two-dimensional vector space, I and j will be 1, 2. Both I and j will take 1 and 2. This is a compact. Now, you see the generalization. If I go to n dimension, there will be n basis vectors, not 2 basis vectors, and it will satisfy this orthonormality condition. So, this is normalized, this one is orthogonal. So, now what we would like to do is, we could also have a non-orthogonal basis, right. So, we call that as psi 1 and psi 2. Why is it non-orthogonal? If you try to find what is psi 1, psi 2, this will not be 0, okay, and psi 2 psi 1 will be in principle the star of this. So, this is the meaning of saying this is non-orthogonal basis. What is the meaning of basis? If I want to write any arbitrary state, I could use, once I call this as basis, I can use some complex coefficients on psi I. For a 2-dimensional vector space, it is 1 to 2. So, this is the superposition of the basis states, which will give you any arbitrary state in the 2-dimensional vector space. So, this is why this forms a basis set, but this is not orthogonal. And then what did we do? We wanted to get to the orthogonal basis from the non-orthogonal basis. This is what we were doing in the last lecture. And some of you were asking me which should be the starting vector. Any of these two vectors I can choose in the 2-dimensional vector space. In an n-dimensional vector space, the starting vector could be any of those n basis vectors. There is no requirement that I have to start only from this vector to do the Gram-Schmidt orthogonalization. Okay. So, just for convenience, we say psi 1 to be proportional to phi 1 with normalization. If suppose this is normalized, then psi 1 itself will be the first vector, and you find the second vector by taking the projection. That is what you do, right? This is what we did last time. So, let us redo it here. So, we defined phi 1 to be psi 1, but this may not be normalized, you have to normalize it. So, we are doing the Gram-Schmidt orthogonalization. Take one of the two states, just normalize and call it to be the first basis vector. How do I find phi 2? Phi 2 will be the second non-orthogonal vector, but subtract the component along phi 1. So, that is what you will do. So, typically you do, this is what will give you the component along phi 1. The inner product of the state psi 2 with phi 1 will give you the component along phi 1, but this is a scalar, you have to get a vector equation. So, I can put the phi 1 this side or I can put the phi 1 this side. Okay. So, this is a number and this is a column vector if you give a 2-dimensional vector space. So, if you are in 2-dimensional vector space, I can denote psi 1 to be AB, and then you can find out factor. Let us give the A and B some specific value, we can take it to be 1 and 1. So, then phi 1 will be what? Is that right? There will be a by root 2 because of the norm. Clear? This is a representation and we use this to find this. So, if I want to find phi 2, I need to take psi 2. So, psi 2 in this notation I could take to be 1 0. If I take that, then you can see this is 1 1 and this is 1 by root 2 1 1 with 1 0. I will give you 1 by root 2. So, do this, and after you do this, whatever is the numerator result, I need to, whatever is this, let me call this to be some new state, and you have to take the norm of that inner product of that state with itself. You understand what I am saying, right? and then take the square root and you should get the phi 2. What do we expect here? What do we expect? We will get 1 by root 2 is what I expect. Can you please do this algebra and check? This will be 1 0 minus 1 by 2 1 1 1 1 with 1 0, right, sorry, 1 1 and then 1 1 with 1 0, is that right? What happens? That is 1 and this is 1 by 1, so you will have 1 by 2 and a minus 1 by 2, right? Numerate, but that is not normalized, right? If you do that, it is 1 by 4, 1 squared plus 1 squared, but 1 by 4. So, this gives you what? Normalization. Someone 1 by 4 plus 1 plus 1, which is 2 by 4, which is 1 by 2, implies square root of n is 1 by root 2. So, you get the state is 1 by root 2 times 1 n. It's very simple. Try to do it for a simple example like this and get a feel of it. But in this process, there is something which I wanted to tell you. What is it we see here? This piece. What is that piece? I just said few slides ago, is an outer product. But what is the operation of this outer product? It projects the component of an arbitrary state along the phi 1 direction. So, this outer product is a projection operator, is phi 1 is a projection operator. It's going to be a matrix operator. If this operates, so let me call this as P1 and put these operators with the hat. This is the convention which we follow. Don't confuse this with momentum. It's some projection operator. P1 hat, suppose I do it on phi 2. What is this? 0 or non-zero? 0. So, that is the definition of a projection operator. If you have n basis set, if you define a projection operator which projects onto a specific basis phi 1, that when it operates on the other orthonormal basis, it is going to be 0. That is the definition of a projection operator. So, you can also similarly define for a 2-dimensional vector space a projection operator P2. You can define a projection operator P2. What is P1 plus P2? The sum of the projection operators should be like a identity operator. In 2-dimensional vector space, I am specifying myself. In the 2-dimensional vector space, the two projection operators can be summed up to be identity. So, whenever I write an arbitrary state psi, I could write this as I said, I could write it as some Ci times phi I. I could also write it as projection operator P1 psi plus P2 psi. Because P1 plus P2 is identity, the state psi is same as this, and this state psi can also be written as a superposition of the basis states with complex coefficients. Now tell me what is C1 and what is C2. C1 will be, P1 is the outer product phi 1 phi 1. What is C1? C1 will be phi 1 with psi. C2 will be the state phi 2 will come here in this outer product. So what is C2? Phi 2 with psi. Okay. So it's, if you understand these concepts in the two-dimensional vector space, for you to do it for any finite dimensional, infinite dimensional vector spaces, this theme is the same. Only thing is the number of projection operator will increase, right? You won't have just two, depends on the number of bases or the dimension of the vector space, and any arbitrary state can be written as either this linear combination or this. Let me stop here.